So this is the 34th session on rigid body kinematics. This is in continuation of the 33rd session. So in this video we are going to discuss the fourth and the last chapter of rigid body kinematics. That is the concept of instantaneous center of rotation, which is shortly termed as IC. Before I go ahead, one thing I would like to make it very clear that if you go through the videos of this channel, they are complete. You have to go through them, you understand them properly, you read them, you understand the theory and numerical properly. You don't have to go to anywhere else. This is more than sufficient. You take up problems from any other source, I am sure you will be able to solve them. In case you have some difficulty, you write it in the comment box. I'll see it and discuss it with you. Okay. One more thing, all the videos on rigid body kinematics have been put in a playlist. Okay. If you access that playlist, all the videos of this chapter will be available to you. So they are complete. Okay. So this I am telling it just for just to remind you. Okay. So we'll discuss the last chapter on rigid body kinematics. That is the concept of instantaneous center of rotation, which is shortly termed as IC. I for instantaneous, C for center. So we are going to discuss the concept of IC, that is instantaneous center of rotation. Okay. So before I define IC, I'll just pick one or 2 points I'll take up just to remind you, because those concepts will be used in this chapter. First of all, you must remember that suppose we are given some arbitrary vector B, okay, and this is some direction along which unit vector is E naught hat. Vector B makes an angle of alpha with E naught hat, this direction. Then component of vector B along this direction is B parallel, say, component of B along E naught hat is simply B cos alpha, and that can be expressed as a dot product B dot E naught hat. By the definition of dot product, B dot E naught hat becomes B into 1 into cos alpha, that is B cos alpha, which is denoted with B11, that is B parallel, say. So this is one thing which I made it very clear. Okay. Now, another point which I would like to emphasize is this. Suppose we are given some reference frame F, okay. M is some rotating rigid body. M is some rotating rigid body. M is moving with respect to F. In general, it's undergoing 3D rotation. Okay. Now, suppose P1 and P2 are two locations of M. Two locations of M meaning P1 and P2 are fixed with respect to M. Okay. So P1 and P2 may be either a real location of M or they may be an imaginary location of M. R is the vector from P1 to P2. Velocity of P1 with respect to frame F at time t is V1F, and velocity of P2 with respect to frame F at time t is V2F. Okay, fine. And omega is the angular velocity of the body with m with respect to frame F at time t. Then we know that V2F and V1F are related by this equation, omega cross R. Okay. So P1 and P2 are two locations of M. That is, P1 and P2 are fixed with respect to M. P and P2 may be real or imaginary locations of M. The V2F and V1F are the respective velocities of P2 and P1 with respect to frame F at time t. And V2F is equal to V1F plus omega cross R. Fine. V2F is equal to V1F plus omega cross R. This is general formula. It is valid for both 2D and 3D rotation of M with respect to F. Okay. In case of 3D rotation, P and P2 any two locations of M. And in case of plane rotation of M with respect to F, also this formula is valid. Okay. The first thing, suppose omega is in this anti-clockwise sense. Suppose sense omega is outward. Okay. See, I express this vector omega in vector notation like this: omega into E naught hat. Alright, fine. Omega into E naught hat. Alright. Now, I take the dot product of this equation with E naught. Okay. I dot this equation on both sides with E naught hat. So V2F dot E naught hat is equal to V1F dot E naught hat plus omega cross R dot E naught hat. Okay. Now what is this quantity? This is just the component of V2F along omega by using this concept here which I discussed here. V2F dot E naught is the component of vector V2F along direction of omega. So let us call this as V2F parallel. What is this quantity? V1F dot E naught hat, component of V1F along E naught. Let us call this quantity as V1F parallel plus omega cross R dot E naught. Now see, this term omega cross R dot E naught can be written as omega into E naught hat cross R dot E naught hat, omega into E naught cross R dot E naught hat. But we know that by the property of cross product, E naught cross R is normal to E naught by the property of cross product. Okay, fine. This I'll rub it, okay. And we also know that the dot product of two mutually perpendicular vectors is 0. So E naught cross R dot E naught hat is 0 by the property of dot product of two perpendicular vectors. So this term goes away. So this term becomes 0 here. So what do you see from this equation? V2F parallel is just equal to V1F parallel. What does it mean? This means that at any instant of time, component of velocities of any two locations of M along direction of omega are equal. If we take any location of M, we get this relation. Suppose that instead of P2 we take another location P3. P3 is another location of M, okay. Suppose vector P1 to P3 is say R1. Let us say R3. Alright. Then if we instead of these 2 points we write down the velocity, we write down this equation for P1 and P3, then what do we get? V3F is equal to V1F plus omega cross R3. Again I take the dot product of this equation with E naught hat. V3F dot E naught hat is equal to V1F dot E naught hat omega cross R3 dot E naught hat. Now this term again drops out as it dropped here. And this quantity is nothing but the component of V3F along E naught, V3F parallel. This is component of V1F along E naught, V1F parallel. So from these two equations, what do we see? V2F parallel is equal to V1F parallel. V3F parallel is equal to V1F parallel. So these three are equal. So this means that at any instant of time, V1F parallel is same as V2F parallel, is same as V3F parallel, and so on. So what does this mean? Tell me. This means that at a given instant, component of velocities of any two locations of M along direction of its angular velocity with respect to F are equal. Let us call it equal to V parallel, say. So this means that at any instant of time, component of velocities of any two locations of M along direction of vector omega are always equal, which is equal to V parallel, say. Alright, fine. Now, we know that any vector can be resolved into its components. Suppose we are given some vector and we are given, for example, I'll just state it here itself. Suppose I take the case of vector V1F. Vector V1F is the velocity of P1 with respect to F at time t. So this can be resolved into two components, a component along omega and component normal to omega. This I'll write it as V1F parallel plus V1F perpendicular. That is how I write it as. So V1F is equal to V1F parallel plus V1F perpendicular. Now this is the component of V1F along omega and this is the component of V1F normal to omega. Now this quantity V1F parallel is just V parallel. V1F is equal to V parallel plus V1F perpendicular. Fine. Now I rub this one. Similarly, we write down similar equations for P2, P3, P4, etc. So, for velocity of P2 with respect to F is V2F, which is again equal to V2F parallel plus V2F perpendicular. Now, V2F parallel is just equal to V parallel. So, this is equal to V parallel plus V2F perpendicular. In this way, we can write for other locations of M. We can write similar equations. So now V1F is the magnitude of V1F with respect to ground. That is the speed of P1 with respect to F at time t. Sorry, V1F is the velocity of P1 with respect to frame F, not ground, F. So V1F is the speed of P1 with respect to F. That can be written as V parallel square plus V1F perpendicular square. Similarly, V2F, speed of P2 with respect to F at time t, can be written as V parallel square plus V2F perpendicular whole square. Similarly, V3F can be written as V parallel square plus V3F perpendicular whole square. In this way, we can write further locations of M with respect to F similar equations. This becomes V parallel square plus V3F perpendicular whole square and so on. Sorry, V4F perpendicular square, sorry. So in this way we can write similar equations for other locations of M with respect to F. Alright. So V4F is equal to root under V parallel square plus V4F perpendicular square. In this way we can write for all the locations of M with respect to F. Similar equations we can write. Fine. Now I rub this one. Now, what I do, I define the concept of IC. Okay. Of IC. IC meaning instantaneous center of rotation. Okay. Of a rotating rigid body M with respect to F at time t. Okay. Definition is this: a rigid body M is said to possess an IC. A rigid body M is said to possess an IC with respect to frame F at time t if there exists a location of M. When we say location of M, meaning real or imaginary location of M, that is, this location is either a real material point of M or its imaginary location. Let us call this location P. Okay. If there exists a location P of M where P is a real or imaginary location of M, such that VPF is 0 at time t. Now this are a bit, okay. This concept which I have written here, it will be used just now. So I am just mentioned it, okay. This will be used, okay. then this location P of M is called the IC of M with respect to F at time t. Okay, so this is the definition of instantaneous center of rotation. IC meaning instantaneous center of rotation. Okay, so what is the definition of IC? A rigid body M is said to possess an IC with respect to F at time t if there exists a location P where P is a real or imaginary location of M such that VPF is 0 at time t. Then this location P of M is called the instantaneous center of rotation of M with respect to F at time t. And instantaneous center of rotation will be termed in short as IC. Okay. So this is called the IC of M with respect to F at time t. Alright. So IC of M at time t is a real or imaginary location of M. Real location of M meaning its material point, and imaginary location meaning its extension point, that is its imaginary location. Okay, fine. In case you have doubt regarding this imaginary and real location, go to the videos on relative velocity. For that also playlist has been made. You can refer to those playlists, then from that you can clear your doubts. Okay. So now that location of M which is at rest with respect to F at time t is the IC of M with respect to F at time t. Okay. Now first of all I would like to say that if M undergoes 3D rotation with respect to F, then M doesn't possess an IC. This point I would like to make it clear. Okay. If undergoes 3D rotation with respect to F, then M doesn't possess an IC with respect to F. If M undergoes 3D rotation with respect to F, then M doesn't have an IC with respect to F. IC becomes non-existent. Why? Reason is this. I'll grab this one first, okay? See, reason is this. A formula which I wrote just now, this is V1F I wrote as what? V parallel square plus V1 perpendicular square. V2F is equal to V parallel square plus V2 perpendicular square, and so I wrote. V3F is equal to V parallel square plus V3 perpendicular whole square. Okay. A V1F is the speed of location P1 of M with respect to F at time t. This V2F is the speed of P2 of location P2 of M with respect to F at time t. Now, in 3D rotation, in 3D rotation of M with respect to F, in 3D rotation of M with respect to F, component of velocity of any of its material or imaginary location along omega is non-zero. That is component of any location of M. When we say location of M, meaning what? Real or imaginary location of M along omega, where omega is the angular velocity of M with respect to F, is non-zero. That is V1F parallel is equal to V2F parallel is equal to V3F parallel, that is equal to non-zero. This meaning, but all these quantities we have denoted by V parallel as I stated at the beginning of this video. So V parallel is non-zero. V parallel becomes what? Non-zero. So see, if this V parallel becomes non-zero, then automatically V1F, V2F, V3F cannot be zero. If this quantity is non-zero, then how can this be zero? This cannot be zero. If this quantity is non-zero, this also cannot be zero. If this is non-zero, this also cannot be 0. This cannot be 0 because this is not square of real number. If this is more than 0, then definitely entire thing becomes more than 0. So in this case, there is no location P of M which is at rest with respect to f at time t. So that means IC doesn't exist. M does not possess an IC. M does not possess an IC. M does not possess an IC with respect to f. Okay. So in 3D rotation of M with respect to f, M doesn't possess an IC with respect to f. That is, IC becomes non-existent. Alright. IC becomes what? Non-existent. Alright. So in this case, IC doesn't exist. Is it clear? So if M undergoes 3D rotation with respect to f, then M doesn't possess an IC with respect to f. Okay. So IC doesn't exist. Okay. Now rub this, okay. So this you must have understood why this V1 parallel becomes V parallel, because in the beginning I stated component of velocities of all the locations of M along omega, they are always equal, which we have denoted by V parallel itself. So in 3D rotation, V parallel is non-zero, so the V1f, V2f, V3f cannot be 0. So there is no location of M which is at rest with respect to f at any time t. So there is no IC of M with respect to f at any instant. Alright. Now, the second point is this. M possesses an IC if and only if M undergoes plane rotation with respect to f. This is the second statement is being stated. Okay. A rotating rigid body M, a rotating rigid body M possesses an IC with respect to f if and only if M undergoes plane motion with respect to f. M undergoes plane motion with respect to f. So it's both ways. If and only if meaning it is true both ways. If M possesses an IC with respect to f, that meaning M undergoes plane motion with respect to f. Conversely, if M undergoes plane motion with respect to f, then M possesses an IC with respect to f. So first what I'll do, I'll prove this statement both ways, okay? So, suppose we take this part, we have to prove both the things as I stated just now. Suppose M possesses an IC with respect to f at time t. Okay. Now we have to prove that in this case, it must be the case of plane motion of M with respect to f. It must be the case of plane motion of M with respect to f in this case. This we have to prove, okay? So how do we prove it? The proof is in this way. See, this is the frame f, okay? This is the reference frame f. F is the reference frame. Alright. This is a rigid body M, which is in plane motion with respect to f. It's undergoing plane rotation with respect to f, plane motion, okay? Suppose this is the suppose omega is the angular velocity of the body with respect to f, assumed to be clockwise for the sake of argument, for the sake of explanation. Alright. Now, suppose this is the IC P. Let this be the IC. Let P be the IC of M with respect to f at time t. Okay. So this means at time t, velocity of P with respect to frame f is 0. Okay. Now let us take some other locations. P1, P2, P3, P4, P5, etc. All these are locations of M. Okay. That is their real or imaginary locations of M. That is their real or imaginary locations of M. Okay. It is being assumed that P1, P2, P3, P4, P5, P, they are all in the same base plane. Okay. So let the vector from P to P1 be R1. Let the vector from P to P2 be R2. Let the vector from P to P3 be R3 and so on. Alright. Now rub this one, okay. So we write down the velocity equation between P and P1. So V1F is the velocity of P1 with respect to F at time t. That is equal to velocity of P with respect to F at time t plus omega cross R1. Now, by assumption, P is the IC of M with respect to F at time t. So this means by definition VPF is 0. So this term goes away. So V1F becomes omega cross R1. Now what does this mean? Omega cross R1 is perpendicular to omega. So that means V1F is perpendicular to omega. Similarly, V2F will be written as VPF plus omega cross R2. But again VPF becomes 0 because P is the IC of M with respect to F. So this term drops out. We are left only with omega cross R2. But omega cross R2 is normal to omega. So V2F is also perpendicular to what? Omega. So what does this imply? If M undergoes plane motion with respect to F, if M possesses an IC with respect to F, then it means what? If M possesses an IC with respect to F, okay, then it means that V1F is perpendicular to omega. V2F is also perpendicular to omega. Okay, and similarly for other locations of M. V3F is also perpendicular to what? Omega. V4F is also perpendicular to what? Omega. Okay, so this means that at any instant of time, velocities of all the locations of M with respect to F are perpendicular to its angular velocity vector with respect to F. So this means all the locations of M this means I write it in here. This means velocities of all the locations of M with respect to F are perpendicular to omega. Where omega is the angular velocity of M with respect to F. But this is the case of plane motion. This is just the case of what? Plane motion. So this is the case of plane motion. M undergoes plane motion with respect to F. Okay. So we have proved one aspect of the theory. That is, if M possesses an IC with respect to F, it implies M undergoes plane motion with respect to F. Okay. But one thing I'd like to say here, I mentioned that P1, P2, P3, P4, P5 are all in the same base plane. That I should not have said that, because there it was not proved that it is undergoing plane motion. Okay, so that statement I just can ignore it. Okay. Just before I reached here, 5 minutes before, I said that by mistake I said that P1, P2, P3, P4, P5 are in same base plane. So that is not true, because now we have till then we have not proved that it is a case of plane motion. So base plane has no meaning. That sentence I just cancel. Okay. Remaining it's all right. So now we have proved one aspect, that if M possesses an IC with respect to F, it means that at any instant of time, velocities of all the locations of M with respect to F are perpendicular to its angular velocity omega with respect to F. And this is a case of plane motion. This is a property of plane motion. So we have proved one aspect of the theory, that is, if M possesses an IC with respect to F at time t, then it means M undergoes plane motion with respect to F. Fine, alright. So one aspect of the theory I have proved it, alright. Fine, alright. Now what I do, the second aspect I will explain in the, okay, I'll write in this itself, okay. So this I'll grab it now. Now we have to prove the converse. Now we have to prove that if M undergoes plane motion with respect to F, then M possesses an IC. This we have to prove. Alright. So this I'll rub it now. Okay. Now we have to prove the converse. To prove the converse, converse meaning what? If M undergoes plane motion with respect to F, then M possesses an IC with respect to F. This is what we have proved. That is, if M undergoes plane motion if M undergoes plane motion with respect to F, implies M always possesses an IC with respect to F. Now we have to prove this. In this case, what I'll do, I will find a location of M which has a zero velocity with respect to F at time t, and by definition that is the IC of M with respect to F at time t. Okay, so what I'll do is that I will, in this case, I will find a location of M. It is a real or imaginary location of M, and whose velocity with respect to F at time t is 0, and by definition that is the IC. Okay, it's something like this. That suppose we are given some polynomial equation x. If we have to prove that it has a real root, I will say by some calculation, I will say that suppose if we replace x equal to 0, LHS RHS becomes 0. Then by definition x equal to 2 is the root, which is a real number. So the polynomial has a real root. So that concept I'll use here itself. Okay, it's something like this. See. So this is the frame F. This is the frame M. Okay. This undergoes plane motion with respect to F. This is by assumption. With respect to F. Okay. Now in this case we have to prove that M possesses an IC with respect to F. This we have to prove. We have to prove that M possesses an IC with respect to F. So what we'll do something like this. See. Suppose this is the IC. Let this be the IC. Let P be the IC of M with respect to F at time t. Alright. Let P be the IC of M with respect to F at time t. This O is some base location of frame F. Alright. Let this P naught be some other location of M. Okay, fine. So this vector R naught is the vector from O to P naught, and O to P vector is R, and P naught to P vector is vector rho. R naught is the vector from 0 to P naught, and O to P is the vector R. Okay, fine. Suppose this is the angular velocity of M with respect to F at time t. Alright, fine. Omega is the angular velocity of M with respect to F at time t. Alright, fine. So now, we have to, P is the IC. See, what we'll do, we will calculate a value of R such that VPF is 0 at time t. By definition, P will be the IC of M with respect to F at time t. By definition, that will be the IC of M with respect to F at time t. Okay. Now, since M undergoes plane motion with respect to F, so there is a concept of base plane is correct here. So let us assume that P naught, P and O are in the same base plane. Let P naught, P and O be in the same base plane. Since M is undergoing plane motion with respect to F, so there is a concept of base plane is meaningful here. So let us assume that P, P naught and O are all in the same base plane. Okay. Now we know from the theory of rigid body kinematics that velocity of P with respect to F, VPF, is equal to velocity of P naught with respect to F plus omega cross rho. Okay. Now we have assumed that let P be the IC. This means VPF becomes 0 by definition. So 0 is equal to Vp naught F plus omega cross rho. Alright. Now see, omega cross rho, I'll bring it to left side. Minus omega cross rho is equal to Vp naught F. So minus omega cross rho becomes rho cross omega, anti-commutative property of the cross product, that is equal to Vp naught F. Now what I do, from this equation you see from triangle law, R is equal to R naught plus rho. R is equal to R naught plus what? Rho. So from this equation we see that vector rho is equal to vector R minus vector R naught, that is vector rho. So this rho I substitute here. R minus R naught cross omega is equal to Vp naught F. Okay. So this becomes what? this becomes r cross omega minus r naught cross omega is equal to Vp naught f. Alright, fine. So this set up this one, okay. Alright, fine. So from this side, what I do, I take this, that side, this. So minus r cross omega is equal to minus Vp naught f minus r naught cross omega. This becomes omega cross r is equal to minus Vp naught f. This becomes omega cross r naught by the property of that cross product. A cross B is negative of B cross A. Now what I do, I take the cross product of this vector equation with omega. Omega cross r minus omega cross Vp naught f plus omega cross r naught. Now this is split by the back rule. We know the vector rule is A cross B cross C is equal to B into C dot A minus C into A dot B. This formula apply in this case. B becomes omega. C dot A, that becomes omega dot R minus C. C becomes R. A dot B becomes omega dot omega. This becomes minus omega cross Vp naught f. Okay, fine. And this is also split by same rule as I split this. This will be equal to plus omega into omega dot r naught minus r naught into omega dot omega. Now we have assumed that P naught, we have assumed that r is the vector from O to P naught, O to P, IC. Now we have assumed that since by assumption O, P naught and P are in same base plane, are in same what? Base plane. This implies, since O, P naught and P are in same base plane, implies that vector R, which is a vector from O to P, that is normal to omega. This is a property of plane motion. Whenever M undergoes plane motion with respect to F, then omega is normal to base plane and vector R lies in the base plane and omega is normal to base plane. So dot product of two perpendicular vectors is 0. So omega dot R becomes 0. Similarly, P naught and O are in same base plane. So vector R naught from O to P naught, that is also in the same base plane. So that means R naught is also normal to omega. So omega dot R naught becomes 0. This term drops out. And okay. So this term becomes 0. This term drops out. Omega dot R naught also becomes 0. This term drops out. So what we are left? Omega dot omega becomes omega square by the property of dot product of two vectors. So that becomes minus omega square R omega cross V P naught F minus omega square R naught. Okay. Now what I do, I divide by minus omega square on both sides. Now I rub this one. So minus omega square divided by minus omega square, vector R becomes omega cross Vp naught F by omega square plus R naught. Okay. So this is the equation of location of position vector of IC, which we have calculated and shown. So R naught becomes R naught plus omega cross Vp naught F by omega square. Okay. So see, this is the position vector of that location P of n, which is at rest with respect to F at time t, and by definition This is the position vector of IC of M with respect to F at time t. So this is the position vector of IC of M with respect to F at time t. Position vector of IC of M with respect to F at time t, and by definition this is the position vector of IC. This is the IC. So we have proved in this case that if M undergoes plane motion with respect to F, then at each instant of time M possesses an IC with respect to F, and at arbitrary instant position vector of IC of M with respect to F is given by this equation. Alright, so R is equal to R naught plus omega cross Vp naught F by omega square. So both the points of the theorem has been fully proved. Alright, so this was the first lecture on rigid body kinematics, on the instantaneous center of rotation. So in this, first of all, what I'll just summarize it briefly. First I said that we defined the component of vector B along some direction as B dot unit vector on that direction. Then I stated that at any instant of time, if M is a rotating rigid body with respect to F, then at any instant of time, velocities of component of velocities of all the locations of M with respect to F along direction of omega are always equal. Then I wrote down the speed of all the locations of M with respect to F using the parallel perpendicular concept. V1F equal to V parallel square plus V1 perpendicular square. V2F is equal to root under V parallel square plus V2F perpendicular square, and so on. Then I defined what is meant by IC. Then I said that in general 3D rotation, if M undergoes 3D rotation with respect to F, M doesn't possess an IC with respect to F. Okay. Then I said that if M possesses an IC with respect to F, if and only if M undergoes plane motion with respect to F, then I proved both the aspects of the theory. Alright. So this was the first lecture. So in this, I hope this is fully clear to you. So if you go through it properly, you don't have to go anywhere else. This is more than sufficient. Alright. And one more thing, all these videos on rigid body kinematics have been put in a playlist. You can go through them, okay? So all your doubts will be cleared. Fine. Alright. So I close this here. I'll continue in the next video on this, in continuation of this concept. I will discuss the 35th video. Okay? So now I close it here.